is orthogonal to the level curve of the given surface. So part A, f of xy is ax plus by. And part B, f of xy is equal to the square root of 1 minus x squared minus y squared. Okay, so for part A, a level curve will look like ax plus by is equal to k for some number k. Recall that a level curve for a surface is a curve of the form f of xy is equal to k. So k is like the elevation of the surface. So ax plus by is equal to k for some constant k. And this is in the xy plane. This is a line in the xy plane. And it will have a slope of, if we solve this for y, we would get the coefficient of x would be, we would have a negative ax and we'd have to divide by b. So the slope is negative a over b. And then we want to say that the gradient vector is orthogonal or perpendicular to the level curve. So if m1 times m2 is equal to negative 1, then lines with these slopes are perpendicular. So we would like our gradient vector to have a slope of the negative reciprocal of negative a over b. So we want that to be b over a. So negative a over b times b over a is negative 1. So let's check that our gradient vector has this slope of the gradient vector. So what is the gradient vector? The gradient of f is f sub x comma f sub y. F sub x is just a. by is a constant with respect to x. And f sub y is just b because ax is a constant, so it has derivative 0. So ab, and the vector ab, this is a, this is b. The slope is the rise over the run. The rise is b, the run is a, so b over a. So this vector is perpendicular to this line at any point xy on the line. And that shows that the gradient vector is perpendicular to the level curve of this surface. This surface is a plane. It's the plane z equals ax plus by. Okay, part B, our function, let's write the function in the square root form here, square root of 1 minus x squared minus y squared. And a level curve means we'll set this equal to k. Now this surface is a hemisphere. That's in the xy plane. And the maximum height is 1, so the number k has to be between 0 and 1. And this is a, let's see, what is this equation giving us in the xy plane? If we square both sides, 1 minus x squared minus y squared is equal to k squared. And we can write this as x squared plus y squared is equal to 1 minus k squared. So that is a circle with center at the origin and radius 1 minus k squared, where k is between 0 and 1. So at any point on this circle, the vector xy is perpendicular to this circle. So if you have a point xy on the circle, then the vector xy is perpendicular to the circle. So we will see that the gradient vector is a multiple of xy. So the gradient of f, let's take this for f here. The derivative of the square root is 1 over 2 times the square root. And we want the derivative with respect to x, so we also have to multiply by the derivative of the inside, which is negative 2x. And then the derivative with respect to y will also have the same denominator, 2 times the square root of 1 minus x squared minus y squared, and on the top, negative 2y. And so this gradient is, the 2's can cancel, 2 over 2. And then we could factor out negative 1 over the square root of 1 minus x squared minus y squared, and we're left with xy. So this is a multiple of xy. And one issue is that this multiple is not valid if 1 minus x squared minus y squared is equal to 1. So that means that x squared plus y squared is equal to, it's not valid if 1 minus x squared minus y squared is equal to 0, which means that x squared plus y squared is equal to 1. And that's along the, this is the unit circle here at the base of the hemisphere. And at those points, the gradient vector does not exist. So everywhere else on the hemisphere, the level surface, so if we take a level surface on the hemisphere, then the gradient vector will be perpendicular to this circle because it's a multiple of a point on the circle, and that's a radial vector. That means it's from the origin to the point xy, and that's a radius of the circle. And the radius of a circle is perpendicular to the tangent line, and so therefore perpendicular to the level surface, or level curve, level curve.